Okay, fine. Yeah. So, yeah, we were talking about how we could form that formula, right? How would we get those equations, right? Yeah. So what I want to do is I want to make V2 such in such a way that it's perpendicular to V1, which is nothing but U1, as I showed in the previous slide. So I take this U2, right? And this is nothing but the V1, let's say, and it has an angle theta between them. I'll consider this parallel component of U2 to be A and the perpendicular component to be B. Okay. What I want to do is I want to get rid of this parallel component because it's parallel to V1. I don't want that. I want something which is perpendicular to V1, and that is B, right? So I get this B. I want to like deduce this B. So now what I'll do is I'll take the component of U2 along V1, which is nothing but A. So that is nothing but the norm of U2 times the cos theta, right? That's just basic vector like manipulations. And then which is nothing but U2 dot V1 by norm of V1, right? Okay. And then we have the vector component of U2 along V1 is nothing but this times V1 cap. And V1 cap is nothing but V1 by norm of V1 again. So, sorry. Yeah. Yeah. So that is that will in turn give us U2 dot V1 by V1 dot V1. This multiplication of norm is equivalent of dot product of V1, right? So with itself. So U2 dot V1 by V1 dot V1. And this is the factor which we are using to scale V1. And that is nothing but going to be A. Okay. And in order to form to get B, we know that A plus B will be U2, right? So B will be equal to U2 minus A. So B, which is equal to V2, because it's perpendicular to V1, that will be equal to U2 minus A, which is U2 minus this factor scale, like V1 scaled by this factor, and that is to V2. So in this way, you can just take a sheet, you can draw the vectors, you can try to deduce other formulas like V3, V4, and then you can see a pattern coming, and then you can generalize it for n vectors. So yeah, nth vector. So that is Gram-Schmidt's orthogonalization. So if you have any doubts, you can just raise it. We'll be happy to clarify them. Yeah. Okay. This is a fairly easy concept. You can try some numericals on this. It'll be available online or we could share it. So, yeah. Okay. I like to try like show you how can we extract basis for any set vector set, not just orthonormal vector set. Okay. So extraction of basis, like okay, fine. I've been given a vector set, but I want to get rid of the useless vectors, and I want to keep only like the I want to form some linear combinations in that vectors for some reason. Let's see. So how do I get this basis? We could use something that we learned in the last linear session. That is the reduced row echelon form, RREF, and we could use that for getting this vector, basis. So yeah, the basic idea is that we take this vector set and we form a matrix out of it. But how? You could do it anyway. We keep all the vectors as columns of the matrix, form column matrices and keep all of them as columns, or you could keep them as row vectors as well. So all the vectors as the rows of a matrix. We'll look at each method. So I will consider an example for this. Let's say we have U, which spans V1, V2, V3, V4, and V5 in four-dimensional real space. What it means is that all these vectors have four coordinates, basically. So V1 will be given as that, V2 is given as that, v3 is given as that, and v4 is given as that, and then v5 is given as that. What we need to do is we want to extract this basis from this given set of vectors. So I mean, you could try it out, but we're sort of running out of time. So I'll just explain like a general idea of how you could do it, right? So if we arrange the vectors as rows and applied the RREF form, so I've arranged all these vectors as rows over here. So we have like 5 rows and 4 columns as expected. And then we apply RREF. You apply all the methods, like do it step by step. That is the best way to do it. I recommend it to be done step by step because you get more clarity. You make less silly mistakes. You don't make silly mistakes, in fact. So like stay calm and do it step by step. And after getting the RREF, you'll get this right here. This is the row. This is the reduced row echelon form of our given vector set U. But what I want to say here is that we get these 0 rows, right? These are the vectors which could be linear combination of these vectors. So linear combination of these vectors will give us these 2 vectors. So like an intuitive way of thinking it, I'm not really sure of that, but we could say like a reduced row echelon form is nothing but you're trying to represent a given vector as some linear combination of like standard vectors, right? The ones that we learned about, standard vectors like 1 0 0 0 0 1 0 0 0 0 0 1 1 1 0 0 0 and so on, like standard basis as we talk about, like yeah. So like standard matrices. My bad. So when I talk about like standard matrices, like some linear combinations if you take, these will be unaffected basically. Like somehow we get these vectors by applying some operations like let's say row operation. You in matrices you have row operations, column operations, scalar operations, right? So we could apply that and we could get these two in like from these 3 basically. So yeah, that is like an intuitive way of thinking about it. You could actually search more on it. I'm not really sure of the intuitive way, but there's like a method to get the basis vector. So these 3 are the basis vectors of our original set U. But what I'm trying to say is these 3 span U. But there is also another solution. We could take all the vectors as the rows. All the vectors as the columns, right? As we can see here, it has 5 columns and 4 rows as expected, and then take the RREF of this. The resultant is different. Does this mean like, am I going wrong somewhere or something? No, it means that both these vector spaces span U. So there are 2 solutions for the basis of U. So it's not like I'm getting one solution correct and one solution wrong, or both are wrong. Both are correct and both span U. So like you could try some examples out on yourself. You can form an example and you can try it. Okay, transformations. Okay, so any doubts you can just send it in the chat. Transformations. What do you mean by transformations? Well, if I change something in my environment, that is a transformation. In mathematical terms, if I change something in my coordinate system, applying some constraints to it, it will give me some other coordinate system. It will be different from my original one, and that is transformation of coordinate systems, or transformation in short. So this is our standard Cartesian coordinate system, right? I will show you some crazy coordinate systems now. So yeah, applying some sort of constraints will give us these coordinate systems as well. I mean, this looks fairly beautiful. Maybe this as well, but this is like pure chaos. But yeah, it's not like we're gonna use it in our general life, but it's still a transformation basically. These are like examples of transformation. But notice how I kept notice how the image has the original coordinate system in gray. The grids of the original coordinate system. That is important to note. We'll come to that, right? So these are like examples of transformations. But I think it is a bit difficult to visualize these transformations, especially this one. Like, how do I even know how to get to this from my original coordinate system? It's like I took my graph sheet and I just made a paper ball, and then I'm looking like, opening it up again. It looks like that, right? Yeah, that's fairly complicated, but there are simpler things that we could learn about, and we are interested in learning about, and that is linear transformations. So linear transformations is like pretty easy to get along with. What are the conditions for a linear transformation is that the grid lines have to remain parallel to each other. Okay, like how in our standard coordinate system they're parallel to each other, x and y directions. In the same way, the grid lines are parallel to the coordinate system in linear transformations. And again, if we are not confused what transformation really means, it means that let's say transformation is a function, and I give an input to this function and get an output. Let's say I give the standard coordinate system as an input. And if there exists a transformation that can, change the or sort of stretch the graph. So you can see over here, it's sort of like I'm stretching the graph sheet, right? If it was elastic, I'm stretching it, and this is how I'll get the coordinate system to look like. So transformation gives us output which looks something like this. So it's basically like a function. So yeah, in that case, I'll continue with this. So like the grid lines remain parallel, and yeah, so grid lines remain parallel, and there is no physical change in the location of origin. Now I'll come to that. I'll come to why is that the case, and I'll prove it. But as of now, just assume that the origin's physical location does not change. What I mean by that is that, as you can see, this is the original origin of the origin, right, of the standard Cartesian plane, and this is the origin of the transformed plane as well. So in this case, the origin has not changed. So I can see that this is indeed a linear transformation. One more important thing to note is that the lines are parallel, fine, but they have to be equally spaced. As you see in our original coordinate system, these are equally spaced. This is 1 unit, 2 units, 3 units, 1 units, 2 units. In the same way, here, this is 1 unit, this is 2 units, and uh, this is 1 unit, this is 2 units, so on. So like they're equally spaced basically. So this is an example of linear transformation basically, right? Yeah, stretching. But what is the intuition behind this linear transformation? Well, I want you to think of the Cartesian coordinate system and think of the vector basis of that coordinate system. So what is the basis of that coordinate system? Well, I can represent any vector as 2 I cap plus 3 I cap, let's say. It's a vector, right? Or let's say 4 I cap plus 5 j cap, or 7 I cap plus 3.888 j cap. In all these cases, I'm multiplying some constant to I cap and j cap, right? What does it mean? Well, I cap is a vector, j cap is a vector. It means that any vector in the Cartesian sheet is a linear combination of I cap and j cap. And I cap is nothing but 1, 0, because it has a unit, its magnitude is 1 and its direction is along x-axis, so it's 1, 0, and for j cap it's 0, 1. So that 1, 0 and 0, 1 is the basis of our good old Cartesian system. Now I want you to consider this point -1, 2, and I'm drawing the vector towards that. What I'm going to do is apply some transformation, put this into a function in such a way that it stretches the graph in some way. Like it's sort of like you mop, right? You're taking a mop which is rectangular, and then you're rolling it and then you're stretching it, right? You're stretching it, or maybe not even a mop. Like you're just taking like some elastic sheet and you're stretching it like that. You're making some sort of changes which is linear, which satisfies all the linear conditions. So the resultant vector turns out to be something like this. Initially, it was like this, somewhere over here, as you can see. It was like somewhere over here. But after that stretching that I did, it's over here. I want to know what is this vector in our original coordinate system. Like if I drew it in my original coordinate system, which would in which it would look something like this, what is that vector? I want to know that. How can I calculate that? Well, one thing to note is that no matter what coordinate system you use, scaling is going to remain the same, right? So let's say instead of like in x-axis, I have like, okay, in this case, it's -1. Let's say I have a vector like 1, 2. So x by you move in by 1 unit in the x direction and by 2 units in the y direction, right? In the same way, let's say I have another coordinate system in which there's apples in x-axis and bananas instead of y-axis. So I have 1 apple and 2 bananas, basically. The coordinate systems are different, but you see what is happening, right? The scaling is going to remain the same. So that is what I'm trying to say. Like, even if you transform a particular, coordinate system, you will transform the vector as well. Transforming a coordinate system will indeed transform a vector, and the transformed vector will be like similarly scaled, basically. Now, how do I calculate this? So, like, if I imagine myself in this new coordinate system where this is the j cap, transformed j cap, and this is transformed I cap, then this is the given vector. So this will be like a linear combination of transformed I cap and transformed j cap, right? This vector, as it will be the same for any coordinate system. It will be a linear combination of its bases. So transformed I is the basis. Transform I and transform j are the basis of this coordinate system, the one that is described over here. So I can say that transformed v cap is nothing but -1 times transformed I cap plus 2 times I transformed j cap, right? Any doubts here? I mean, you can mention, it'll be clarified. So yeah, this is like the basic idea. So yeah, I just represent this I cap with v vector and j cap with w vector. And for example, let's say the transformation is in the j vector is 3, 0, and I vector is 1, -2. Now, okay, transformed I vector or transformed j vector basically means that in that imaginary coordinate system, the j direction is along this vector that we consider in our coordinates, like standard coordinate system. So in our standard coordinate system, it will be in like this direction, right? It will go this way. So wait, sorry. In our standard coordinate system, it will go like this way. Yeah, my bad. So that this way, right? So that is going to be our new x-axis, basically. And 3, 0, which is like our new y-axis. So that will be like this way. So this is the y-axis and this is the x-axis newly formed. So I could represent the transformed vector like this. Okay. So the resultant vector then is nothing but this transformed vector. And we know how we represent v cap, v vector and w vector in our coordinate system, which is just what I told over here, right? So we do that calculation over here. Basically, it's all that we do. And this looks, so we do these calculations and we get phi 2. Cool. Okay. But this looks familiar. This looks like matrix multiplication. And what are the matrices that we are multiplying? These are the matrices that we are multiplying together. Do you note something? Yeah. This is the original vector that we come up with over here, right? And this is a matrix in which the columns are the basis of our new coordinate system, or our imaginary, like not imaginary, but new coordinate system. Oh, so usually this matrix is called as a transformation matrix, because when we multiply our vector with this, we transform it to another coordinate system. We get to know what it looks like in another coordinate system, which has the basis vector as these columns. So that is basically linear transformation. And yeah, we have the textbook definition as usual again. Here it could be a bit difficult or hard to read. So I'll just quickly run through it. If V and W are vector spaces, like just like V can be our coordinate standard coordinate system, and W can be a new a new coordinate system that we saw in the previous example. And they over the same field F, which could be real or complex, and the W, that is, we can map a vector and weight to W. So anything that is in like V can be mapped to W. It's said to be a linear transformation. So as I defined linear transformation as function, right? So T here is the linear transformation. So it's a like it can be described as a linear transformation. These conditions are literally what linearity means. In general, if you say anything, like say linear equations, you know, in like if you take like linear equations or anything linear, always these conditions come. So if there is a function which involves an input as a sum of two entities, it will be the sum of the function of those entities individually, right? So T of x plus y will be x of y, and T of, if you scale the input, the output will be the scaled version of the original output. So T of alpha x will be equal to alpha times T of x. So yeah, this is just the textbook definition. You can just look at it, take a screenshot, you know. So yeah, that's linear transformation. That's it. So I want you guys to think of linear transformation as a language, right? It's like a language, not just a mathematical concept. It's a language, and transformation as oh wait, I think I made a typo over here. I'm sorry. I wanted to write transformation matrix. Sorry, transformation matrix as a translator. Just a second. Yes. Yeah. I want you to think of transformation matrix as a translator. So whatever the language be, with this transformation matrix, I can translate it back to my language, which is, or I mean, I can translate to the other language. I can translate it to the other language. What is the language here? From my standard coordinate system, I can translate it to the new coordinate system. So in transformation matrix has all the information that you need for this translation. Cool. Okay. Just a second. Right. So that was linear transformation. Now we quickly run through the basis transformation. Yeah, so learning about linear transformation is fine. Basis transformation, what does it mean? We'll look at it. Let's say we have a vector 3, 2 in the standard coordinate axis. What I do is that I want to represent this vector, if I use a different vector basis, like for this, the vector basis is 1, 0 and 0, 1, right? What if I use a different vector basis? What does the vector look like then? I mean, it's similar to what we did in linear transformation, right? So again, I would like to look at it. So what does it look on a different base vector? Okay, I want you to think of this ridiculous scenario. So you have a friend from Vietnam, okay, and he doesn't really speak English, but you're somehow friends. Um, so you prefer to use the standard coordinate system, whereas your friend has a different coordinate system, which is not the standard coordinate system. Now you guys plan on meeting up for the first time. So he sends you his coordinates as -1, 2. So you take a long walk and then reach his coordinates just to find just to find yourself alone. So what happened? Did he like ditch you, or is he playing a prank on you by giving you the wrong coordinates? What's going on? Well, I think it's quite clear what is going on. And if it's not let me explain. So he gave the coordinates in his coordinate system, not in yours. In yours, it could mean a completely different location, and in his, it is a completely different location. So how do I reach his coordinate system without being a pain for him? Well, I could just ask him like I could just use my translator for this, right? So yeah, as you can see, we need to implement some linear algebra to get to his coordinates, to get to his location. So let us say that his basis vectors, instead of the normal standard basis vectors, it is b1 and b2. And for him, this image might be a bit misleading, but for him, b1 will be 0 2 1 0 and b2 will be 0 1. This is for him. It's not with respect to us. This is from his perspective. So this is what it would look like in his system. So a key thing to note again here is that the origin will be the same, at least in the case of linear transformation. Why? Because origin means nothing but scaling any vector in the coordinate system by 0. So you multiply any vector by 0, you'll get to origin anytime, right? So in any coordinate system, whatever the direction of vector is, whatever the vector is, you multiply it by 0, you'll get back to 0. At least in the case of linear transformations. So yeah, the output will always be 0. So that is one thing to note here. So in both of your coordinate systems, origin will be the same. The location of origin is going to be the same. So it would have been much convenient if he was in origin, but anyways, he's not. We need to come up with something to get to his location. Another important thing to note again here is that scaling the vector in any coordinate system will make similar changes. What I mean by this again is that, as I told you, I cap and j cap are linear combinations, right? I could scale them to form a vector. Similarly, b1 and v2 are the bases. So I could take the linear combination of b1 and v2 and get a vector, and it will have the same effect. As I told, like -1 and 2 in the previous example, -1 and 2 were the coordinates in my standard axis, right? In the new coordinate system as well, -1 and 2 will be my coordinates with respect to that new coordinate system, with respect to that. So again, scale will make similar changes. So if b1 and b2 are the vectors that our friend considers as the basis vectors, we could use this language that we came up with, that is linear transformation, to extrapolate like his meaning of -1 2 and meet him. So you need a translator again, right? So, but I want you to think of, I want you to walk through an intuitive approach to this. I don't want you to apply a formula. I don't want you to give I don't want to give you a formula. I'll tell you how to get to that formula. So for a coordinate system, like again, we consider b1 and b2 as the two vectors, and these b1 and b2 are the vectors in my language or your language, let's say. Again, I'll use this word language often to sort of give you a perspective, and it makes it easy to understand. So b1 and b2 is in your coordinate system, right? b1 is some direction in your coordinate system, b2 is in some direction in your coordinate system. And well, I could use this language to get to the result, like to the that he is referring to as -1 and 2 by reverse transforming it to my language, basically, or my coordinate system. So I want to see where does this vector that he is referring to as -1 2 land in my coordinate system, so I can go there. So again, here b2 and b1 is what this is like the basis of my friend's your friend's coordinate system. So these grids are like our coordinate system, standard ones. b2 and b1 are given to us. That is his coordinate system. And this is this, like, you just have to scale it. So b1, you just do minus b1 in this direction, and you scale b2 by 2. So you get this as the resultant vector. This is the resultant vector in the coordinates, our coordinate system. This is where we have to go. And that's just a simple algebra. The resultant vector in our coordinate system will be -1 b1 vector plus 2 times b2 vector. And we know, we just asked our friend what his basis vectors are in the coordinate system, and he gave it to be this. Again, it sort of doesn't make sense, because how will he know what our coordinate system is and give us the basis vector? It's like in a hypothetical situation where he somehow knows this information and all, right? So yeah, Don't try to bring that up. It's just a hypothetical situation. Right. So he gives us this information, or we somehow get to know this information by our big brains. And yeah, we apply the for this simple algebra and get the resultant vector to be -4 and 1. That you can see, I scale it -4, and this is 1. So that is where he's standing with respect to our coordinate system. So if you go there, you'll be able to meet your friend. And again, this is like an example of matrix multiplication. And this is indeed a linear transformation, right? So this is, of course, a linear transformation. Here, this is our original vector, and this is the transformation vector, or the translator. I like to call it the translator. Right. So applying linear combination on any vector will give us the transformation, like by the transformation matrix. So, yeah. But what if you want to give your coordinates to your friend? Do you apply the same transformation? Don't be misled. You can't really apply the same transformation. Because like if there's a way you can if there is a function that can be used to transform from your language to his language, then the inverse of that function only can be used to transform from his language to yours, right? You get what I'm saying? So from his language, this was the translator. From my language, this won't be the translator. The inverse of this will be the translator. That is a key point to note here. So you need to find the inverse of the transformation matrix. You can do the same steps again, but I'm just like this, like you get like this sort of like common sense now. Like if you wanna revert back the process of from giving your coordinate system to him, and again you want to save him the trouble of all these computations and all. You're trying to be a nice friend, so you take the inverse of the transformation matrix and then give it to him. Right. So this is your location in the coordinate system. Let's say 3, 2 is yours. Okay. And this is like what it looks like in his coordinate system. Now you need to find what this vector is in his coordinate system to tell him where he has to come, right? So again, you have all you have to do is just find this inverse of the transformation matrix. Let's call it F. So you just find this inverse of the transformation matrix, and then you just try to imply that. So this inverse turns out to be this much. As I told you, like inverse of a matrix, I hope you try to go through how we calculate the inverse and determinants. But if you haven't, it's not a problem. Inverse is just you can try to go through it. I guess it's easy only. So you can take the inverse of the matrix, the transformation matrix, and then the given, like where he has to come is this the inverted matrix times the vector in your coordinate system, and this is exactly the location where you are in his coordinate system. So you tell him to come to this coordinate system, and then you can have your little meet.